So let's go in and dive into steam. All right. So after all this time, what they made you memorize during INDOC has finally come to pass. The steam water cycle. All right. So we're going to basically break it down into these 4 sections. All right. We have over here, we have our generation, where we are actually utilizing all the energy that we've made from our generation. We have our condensate side, and we have our feed water side. All right. So it's those 4 main pieces are going to be broken down. Okay. So as we go through, we have our boiler to our superheater. And from our superheater, we break off from our main steam, our TG, and our auxiliary. It all comes from the same place, even though they have 3 different names. All right. From there, it goes to the high pressure turbine, to the low pressure turbine, right to the main condenser. All right. From the main condenser, it goes to the main condensate pump, air ejector, first stage heater. You got the DC heater, main feed pump to the economizer, and back into the boiler. All right. So with that being said, if all of our energy is just being used, and this is all we care about here and here, because this is what's producing and propulsion being our ship's propulsion. And then we have our electricity. Why do we care about this bottom half? What's the point of that? Efficiency. What else? Not just efficiency, but what else are we doing? Think about the other subjects that we went through this entire semester. You know, we like to throw that word efficiency around, but what else have we done?
Recovery.
Recovery of what?
It's boiler water.
Of all our boiler water. All right. Think about how much time and how much effort went into making distillate. All right. And if we were to just take this, and we can go right from the low pressure turbine and just dump it to atmosphere or dump it to the seawater, and it doesn't matter, all this efficiency is lost. All this feed water that we made is now gone. All right. So let's get into it. This side over here is all vapor. For some reason it doesn't want to. One second, guys. Just acting up. All right. There we go. So that side is our vapor. All right. And then we have our whole liquid side over here. All right. So let's take a look at our pressures. All right. What's the first thing that we're seeing based on our pressure right here?
Going down. Pressure's going down.
Pressure's going down. But what else? What's a big thing that we notice? Where is we have our power generation on one side, and then we have what on the other? We have our boiler being our power generation. And then on the other side of the system, we have what we're using that power generation for. all that force is being applied to turbine blades. But looking at our pressures, what's on the other side of it? Just on the other side of these low pressure and high pressure turbines.
In a vacuum.
It's going to basically a near perfect vacuum in our main condenser. All right. So look at this pressure differential that we're having here. We're going from 600 psig to basically a near perfect vacuum. Think about that drawer that's going through it. So it's not only just a high pressure. This would be high pressure in just this atmosphere. But the fact that we have a vacuum even sucking it through, it's pulling it as much as it's being pushed through the system. Okay? Big thing to recognize is too, look here and here. What else are we seeing? Along with our pressures.
Temperature drop, or temperature increase.
Temperature increase. But why is that? What's happening in between the two?
Pressure drop.
Heated.
Well, we do have a pressure drop, but in all reality, we do call this 600 psi. That's our 600 steam line. It exists here, but we still call it at 600. But what is really going on? What's happening in between this 600 psi marker? Say again?
Superheating.
So what's the superheater do?
It heats it past its boiling point.
Well, we're already past its boiling point here at 490 at 600 psig. What are we doing?
It heats it to the point where there's absolutely no vapor. It's only superheated vapor.
Exactly. So remember what we talked about with water generation. What is the big thing that you need to do when we start talking about our whole steam water cycle scale, right? We have a solid, then we have a liquid. Oops, those are backwards. Those are liquid gases. Solid down here. And gas. And then these are the mixtures. What have we talked about that happens at these points? If this is just at 14.7 psig, normal atmospheric, what is its boiling point for water?
212.
Yeah. And then at solid, it's 32. But what is happening? What are we changing on this line?
Latent heat.
It's the latent heat, and we're adding energy, right? So as soon as we go into this gas state, we are now increasing in temperature. So what happens as soon as we make this curve? As soon as we go from this point to this point on this graph, what do we no longer have present?
Liquid.
We have no more liquid. All right. And that's the thing that we have to keep in mind here. When we go through this superheater, one, in the boiler, there is a baffle. that does not allow moisture droplets that are entrapped in the vapor to go through. And I know we talked about this steam. This superheated steam is invisible because it has the lack of water molecules entrapped in it. All right, so that's something to keep in mind of what's happening. These are at high temperatures and high pressures because of what's happening inside the superheater. All right. So let's move into just the generation part. Drum type. So this is what the inside of the boiler looks like. All right. This is normally how you'll see them drawn. Sometimes you will see a little box down here instead of a circle. It means the same thing. All right. If you look at it, we have over here, we have our burners. We have a huge mass of tubing all inside of this. During Mud Cruise, we're going to go deep into all of these, but for now, let's just label a couple. All right. So first of all, we have our air and our fuel, because any sort of flame needs fresh air in order to burn. All right, so our fuel goes through our burner tips. Our air is drawn from in between the boiler and the sidewall of the steel. So it's preheating the air basically. You have your flame, and this is where it's actually burning. All right. You're not going to have flame all up in here or anything in like that. This is where it's basically going to stay. It's going to be a cone shooting out of your burner tip. All right. So up top, we have the steam drum. On the bottom, we have the water drum. Now, same thing goes over here. Up here, that's our steam drum. Down here is our water drum. All right. And then this over here is called our mud drum. And that's going to be located down in this spot over here. You can actually barely see it there. Right there. It's a little tube, basically. So you have these generating tubes on either side. You can see they're connected from here down to the water drum, and then to the side of the water drum here, up to the side of the steam drum up here. But keep in mind, these tubes that I'm outlining right here are not part of your generating tubes. All right. The tubes that I just highlighted in black exist in between them, but they are not connected, and they are not considered your generating tubes. Now you have your water wall tubes. So, looking at all that, before we move on, what is the point of our generating tubes? What do they do?
Generate steam.
So they're generating, they would be generating the steam. All right. What else? Why not just use just the steam drum and just have a flame directly underneath it? Just call it a day. It would be a lot simpler to build.
But that's saturated steam.
Well, we don't have, in here, we're going to have saturated steam.
Surface area. It's a lot easier to heat up a bunch of tiny tubes than just one big old pot.
Exactly. Right? Just like when we were talking about the plate type heat exchanger. It's all about the surface area. Right? It's the same reason why we have all the coils in our air conditioning units. It's the same reason why we have your, basically if you had a big furnace in your house and you use steam in your house to heat your house. All right. It's the same reason if you have, oh, come on, you stupid thing. If you have baseboard heating with all of the fins on it, it's to increase your surface area. All right. So over here we have our flames. Like I said, they kind of stay in this spot. You know, they're not going to be licking all of these tubes over here or anything like that. They're not going to be coming in, but it is going to be spreading its heat everywhere. All right. Just because there's not a flame in this spot doesn't mean that it's not hot. All right. This whole boiler is extremely hot. And this is kind of the big thing about this is with steam boilers. This is the theory of how water travels in it and how steam is traveling through it. All right. For one, we have our hotter side over here. All right. So the cool is going to go down and travel back up this side. It's going to get heated up and move back up. But if you start to take a closer look on the inside of these tubes, and as they raise up, all right, your steam drum is half filled with water. Your water drum is completely filled with water. All right, and if your steam drum is half filled with water, do you think you have one-way valves here? Or over here, or over here, or over here? Are we going to have directional valves?
No.
No.
Wouldn't it just be directed by the difference in temperature?
So yes, it's not going to have any directional valves. It's going to be determined on difference in temperature and how all of liquid moves inside of it. But what is happening? So if we're generating steam, what's happening then? What's keeping our water level in our steam drum? What's keeping it at half? If this side is creating steam and all these tubes are generating tubes, what's going on? How can we have a steam drum that's half filled with water and yet are we producing steam on this side? How is steam holding up a column of water?
The water in the steam is condensing.
The water in the steam is condensing. So what happens to that energy? What happens if this
Recycled
tube
through the boiler?
Say again?
Is it recycled through the boiler?
So is it going in this direction and just constantly flowing in a... Are we producing steam at this moment every single time? And it's steam from here to here? I'm getting very messy in my drawing. Are we getting steam from here to here always?
I mean, it's not really a column of steam. It's more a column of water with a lot of steam bubbles, is the way I was told. But
That's exactly right. All right. And that's the biggest thing you guys have to recognize with this. It's not, there is with boilers and everything that has to go with it, there's not a huge amount of know exactly where the point where it turns exactly into steam. All right. So inside of these generating tubes, you will have basically a column of water that's really hot. All right. But you're going to have steam bubbles, and they're going to be going up, and they're going to be doing what? What is steam different from water? What makes it different? Not only just its state, but what about its energy?
Higher energy.
It has what?
Much higher energy.
It has a higher energy, all right, due to temperature. So as the steam bubbles travel up the generating tube, they're going to be heated up by this flame. But what else are they doing? What are they surrounded by?
Surrounded by more water.
Surrounded
So
by
it's
more
heating
water
up.
that's lower temperature. So as it travels up, it's heating up the water that's surrounding it. So you may have a steam bubble that travels an inch and then turns back into a liquid, giving off its energy to other water around it. And it's just going to constantly be, maybe you even have a little bit of a circulating steam bubbles that are just happening in these little spots, where they become steam. They start going up the path of through the water faster. And then as they go up through the water, they give off their energy, and then they become water again. So they slow down, they start to become water, and they go off the flow, and they fall off basically. And then other water molecules that are a liquid, they become steam around it, not only because of the steam that was inside of it, but because of the flame. And then they become steam and then travel up faster. So it's just this constant process of very small molecules becoming steam, turning back into a liquid, then they turn steam into again, and they're just constantly going up this whole entire generating tube that create this flow. There is no exact point where, oh, from here to here is steam. All right. Does that make sense? Okay, good. I thought that was like the coolest thing when I first learned that. I think I was on Mug Cruise when I first learned that whole process. All right. So like I talked about, this tube right here are not part of our generating tubes. They're our superheater.
Why did you have the superheater outside of the boiler in the other diagram?
That's basically just so that way it represents it, and it's through your cycle. Okay? Even though it's not physically outside of it, it's one of those things where your superheater is a different, almost different component. And it's to be known that it's next after the boiler.
Thank you.
So why, if our superheater is going to be, one, increasing the temperature, two, it's also going to be removing all of the, it's just going to, making sure that we have no liquid present. Everything is that is completely dry steam. So why are we keeping it far away from our flame? If our flame is over there. Why are we keeping it far away?
It's the superheater tubes because they're smaller and they'll just melt or something.
So they don't have any liquid in it. All right. So they're not necessarily being cooled, the tubing. All right. It could take the heat, but not a direct source.
Is it just steam in there?
It's just steam in there. All right. The superheater has only steam. There's actually a baffle here that keeps any water molecules from entering if they're getting dragged up through the steam. All right. The superheater is going to superheat the steam. It's already at 600 psi, but now we're increasing the temperature to ensure that there is no water molecules present. No liquid molecules can be present in this. All right. Just like what's going on into our compressor of our refrigeration cycle, if a water molecule impacts a turbine blade, there's extreme damage that happens. You'll learn about it in your turbines class and everything, but there is a huge amount of damage that will happen. And that's what we're doing. We're protecting our turbines. So we leave the boiler. Oh, and by the way, has anybody actually been, while it was open, did anybody get a chance to go in there? A couple people? While the ship was off? What would it feel like in there? Standing in that spot? For the guys who were in there. Even while the engine room wasn't running, what was going on in that spot? You guys have microphones or?
It was like hot in there.
Okay. One, it's really, really hot in there. And two, what about the space? When you're standing in there, what's it feel like?
Small.
It's small, right? You're pretty much up, your back is up against the tubes, and you're pretty much right here with the tubes right in your face. All right, it's a very small area. But if you get a chance to go into it, I highly suggest it. It's actually really interesting to see all the tubes that close. So as we go through, we have now left the boiler. We are at superheated steam, 600 pound, and we leave to go to our three main lines. We have three different valves. All right. We have our main steam stop valve. We have our TG steam stop valve. And we have our auxiliary steam stop valve. Again, like I said, we're engineers. We like to have control. And this gives us the ability to determine where and direct where our steam goes. And then we have our superheated safety valve. And then we have our superheater vent valve. Oh, and by the way, everyone, these slides will be up this afternoon. Okay. So as we go through, we are done with generating all of our power. We are now transmitting into actually utilizing the steam. All right, so we're going to go into our high pressure turbine first, and then from there we go into our low pressure turbine. So we have what's called an axial flow turbine. All right. This is basically how it's producing. We have a nozzle right here. We have our steam pressure coming in. Can you guys see this black all right, or the black?
I like the red better.
Yeah.
The red was better? You guys gotta let me know this. That's better? Okay, good. So this blue line right here is our steam velocity. All right, so as it comes into the nozzle, it's constantly increasing, and as soon as it leaves the nozzle, they're in line with each other. It peaks, it plateaus. Now, what is happening from here to here, though, that we're losing our velocity? What's going on?
moving the turbine blades, and the turbine blades are slowing it down.
Yes, exactly. All right. Now, on the other side, we have our steam pressure. All right. We start out right before we go into the nozzle at a high pressure. And as soon as we go into that nozzle, we start losing pressure. All right. And it's happening at the exact same time as we're gaining our velocity. All right. Our velocity isn't just the created energy that we are making. We are transforming energy. All right. So we're utilizing our steam pressure to create steam velocity. So this is our high pressure turbine. It's a 3-stage impulse turbine.
This part always confuses me. Is the blades the half? Oh, okay. The blades are the not the half moon things.
Yeah, so that the blades, every blade of the turbine are represented by these half moons. All right, all the red arrows are showing the blades of a turbine. All right. And these are our nozzles. So the nozzles are completely stationary. They do not move. All right. They're attached to the turbine casing, but the blades do. The blades move, fitting in a wheel attached to the rotor shaft. So a stage consists of a set of nozzles and a set of blades. All right. So we have, that would be one set, that's another set, and that's your third set. So that's your 3-stage. So basically, as steam comes in, we're losing power. All right, we are losing pressure. So, but that's fine, and that's why we're gaining what we're trying to do, which is try and move and propel the ship forward. All right, so as you can see, the steam is expanding as it goes. So when we're losing power to gate the same amount of spinning speed or to still push on the turbine blades with the same amount of force, what we need is a larger turbine blade. And you see our smaller blades are with us less energy loss. So we lose the same amount of energy in every single one of these. But what's happening is we have a higher pressure here. Then on the other side of that, we have a little bit less of a higher pressure, but we increase our blade. And what we're going to gain is that we're going to gain more force being applied to a larger blade. All right, so it's going to basically allow us to exert the same amount of force, even though we have less force to give with the same amount of volume of steam. All right.
So do we have an impulse turbine or an axial flow turbine?
We have an impulse turbine. So this is basically the shaft that is spinning, not the shaft of the ship, but this is the shaft that is spinning inside of our high pressure turbine. All right, so this is the actual casing that you would see. why turbines are drawn that way. All right. So what is going on here is we have a set of gears. All right. And these gears, if we notice, one is we have a pinion gear right here. It's smaller, and then we have a bowl gear. We'll get more into that in a bit. But just recognize they are geared into our main shaft of the actual ship. All right. Come on. So this is how we're actually arranged on board our vessel. We have a high pressure turbine casing. We have our low pressure turbine casing. All right. Our head steam comes through our high pressure turbine casing first, and then it will cross over into the low pressure. But only a stern steam goes into the low pressure turbine casing. It does not go into our high pressure turbine casing.
Which turbine directly spins the shaft of the ship?
Both do. All right. So when you are going ahead, both the low pressure and the high pressure are geared into the shaft of the ship. When you were going astern, the high pressure turbine casing is basically just going for a ride. All right. Only the low pressure turbine is actually forcing the ship to go astern. Okay. Man. So we have a high pressure turbine. We have 9 impulse stages. All right. Remember, a stage is a set of nozzles and blades. All right. We have our steam chest where all of the head steam is actually entering. We have our crossover at the end going to our low pressure turbine. So when we were going ahead, normal operating conditions, a head steam is entering our steam chest. It travels through all of these blades, and it goes to the low pressure turbine, and then it goes through all the low pressure turbine blades. All right. All of these high pressure bleed, an IP bleed, crossover extraction, all of these valves are utilized in startup. All right. For now, just recognize that they are there. So our low pressure turbine looks like this. We have 4 impulse, 1 transition, and 4 reaction. Now we have our stern portion of it. And our low pressure turbine is basically broken up into 2. All right. Our stern turbines have 1 Curtis and 1 impulse stage. All right. So we have our 4 impulse, 1 transition, and 4 reaction. This is our head, and our stern have 1 Curtis, 1 impulse stage. So this is our crossover that's coming from our high pressure turbine. All right, so we have steam coming from the high pressure side. And what we have over here goes right into our condenser. All right, so the steam is going to travel from our high pressure turbine through the high pressure turbine, through our crossover, into our low pressure turbine. It's going to go through all of these blades and get sucked into our main condenser. When the astern steam is on, oops, skipped it. We travel in this direction. All right, we are going to be rotating in the opposite direction. All right, ahead was going this way. Astern is in the opposite, and they both go right into the main condenser. So let's talk about nozzles and control valves. So we have C speed. C speed is long duration, it's port to port. All right. As opposed to maneuvering speeds, this is what we're going to be using to go across for long extended periods of time. All right. We have a throttle at a fixed position. It's usually wide open with our nozzles. So the nozzle control valve opens a chamber to a set number of first stage nozzles. All right. So our high pressure turbine casing, our steam chest, remember, is what's getting all of our 600-pound steam. All right. So these nozzles right here, these 1, 2, 3, 4 nozzles, will control how much steam is going to be entering our steam chest. And the number of nozzles open correspond to a particular engine RPM and hence C speed. All right. We're going to go into depth of the nozzles in a second. So those numbers correspond to something. All right. So each one of these nozzles are coming in. We have steam coming in this direction. All right. 9 and 12 are opposite. And the big thing that we're noticing is that we can have multiple nozzles open. All right, and when the nozzle's open, the steam is going to be entering and coming in and going into these sections. All right, remember these correspond to a specific RPM. So in order to gain a certain RPM, we can utilize these nozzles that have different numbers to them. The 9, the 14, the 12, the 4, that we can create different RPMs utilizing those nozzle numbers. All right. Does that make sense to everybody? Okay, cool. So as we go through, we have some very important control situation right here. All right. We have the ahead throttle and we have the astern throttle. Where are those located in the engine room?
Aren't they on like a control panel?
They are on a control panel, but where?
Throttle box.
Say again?
Throttle box.
It's on the throttle box, yep. But where is that in relationship to?
Behind the turbines.
So they're behind the turbine. So as soon as you walk into the engine room, you're basically walking past the throttle box, right? So where is the astern guardian valve then? Where is this?
Above the throttle box to the left.
Yes. All right. So what's the point of these? What are we trying to do with all three of these valves? What's the ahead throttle do? Let's start easy.
To regulate how much steam is going into the high pressure turbine.
Correct. So that's what the ahead is doing. The ahead lets a particular amount of steam to go through from our boilers. All right. We open it up. We get an increase of speed and more steam is going through. All right. We use more steam. We need more steam to be produced. So we close that ahead throttle. Now let's talk about the astern. What happens if we open the astern right now?
Nothing, because you got to open the astern guardian valve.
Exactly. So what's the astern guardian valve do?
Prevents the both astern and ahead like being on at the same time.
Exactly. It's the protection. All right. So if you open up that astern guardian, you need to have the astern guardian valve open as well. The astern guardian valve needs to be fully open. Now then, that is just pretty much turbines and throttling with them as simply as we can get down to it. All right. Does anybody have any questions on this before we move on to the next section?
What would happen if you just opened all of the nozzles and just full steam?
She would run at full steam, but she hurts when she does that. All right. You know, she's old, but she can go all nozzles.
Doesn't the ship rattle when it goes full speed?
It only started rattling when we went from. So I was on board when we went from full ahead. So we did sea trials with it my senior year, and basically we went from one. They kicked us all out of the engine room because they had MARAD on, and they didn't want any cadets in there when they were doing these testings, which was unfortunate. I think they just kept the boiler cadets in with them. But basically, they did is they went from full ahead, and after full ahead, they went to they wanted to see our max speed, and they wanted to see how long it would take us to go from max speed to before we started making momentum backwards. All right. So they had all nozzles open. We were running fine. The thought process was that the ship would start to shake. It really didn't shake. The only point it did start shaking was, and it was only really heard when you were on the stern and back on the fantail, was the fact that when they went from trying to go from full ahead. They closed the head throttle and they opened up the Astern Guardian, and you hear the propeller stop in the middle of the ocean. And then all of a sudden you hear it start slowly churning the water and trying to stop a massive ship from going where it was going full sea speed to trying to go in reverse. And that's when this thing started to shake. It was fun. It wasn't dangerous, but it was just really interesting to see this thing shake and go a little nuts. I think the time was like, it took like 10 or 15 minutes before going from full ahead to finally starting getting momentum backwards. So a full 10 minutes.
Why'd you guys do that again?
They're basically checking to, I think they were recertifying the vessel. But it was, it's sea trials. You'll have to do sea trials every once in a while on ships, depending on certain things. Obviously, when it first launches, the first time it goes out, they test everything to ensure that it's all working. Usually the next times they do a smaller version of sea trials, but it still has to be done with the Coast Guard, is whenever you do something with anything of your controls. All right, so when we put in a new control system on board the Empire State, so all that stuff for the boilers, they had to do sea trials after they installed all those control pieces. One vessel we were getting certified to go back to that I was on, we went from being a manned engine room back to an unmanned engine room, which basically, as we talked about, means that they have no one standing a watch there all the time. We had to go on sea trials with the Coast Guard for a couple hours just to make sure that our controls that we implemented would be satisfactory to them. So you can do sea trials for any number of things. All right. Any other questions? No? All right. Let's continue on to the condenser. So we are utilizing on the TSES a shell and tube type heat exchanger. All right, which basically means, as we talked about, all the hot stuff is coming through the top and all of our salt water is flowing through the sides. All right, from the side of it, it looks like basically, if you're looking on this blue side here, it would be filled with little tubes all the way through. Not going to draw them all out, but that's basically what you would be looking at. And all of those tubes represent one of these tubes that you're seeing here. All right, so they do not make contact with each other. They're separated by copper, metal, some sort of element with anything of what they decide to build it with. All right. But we have steam coming through here, and we have condensate coming out the other side. And this is all salt water going through here. So like I said, fluid 1 gives up the heat, which is our steam. Fluid 2 absorbs the heat from fluid 1. That is our salt water. Either fluid 1 or 2 may be the primary fluid. Either fluid may be inside or outside too, but there's no direct contact. All right, so we could be doing something different with a shell and tube type heat exchanger where we don't want, our main goal isn't to cool down steam to a liquid. We may be wanting to just heat up glycol like we were doing with our Nyrex. All right. It all depends on what your main goal is with these things. So with a shell and tube type heat exchanger, the heater is a primary fluid, does not change phase, but increases in temperature. It's sensible heat. All right. A cooler, a primary fluid does not change phase, but decreases in temperature. So we have two examples there. We have our fuel heater and our lube oil cooler. So if it's a shell and tube type heat exchanger and it's a heater, the primary fluid does not change a phase. It's only increasing in temperature. So if we have a really, really thick fuel that we need to heat up in order to increase its viscosity and move it around the ship, that would be a heater. And a cooler is trying to remove all the engine heat with our lube oil cooler.
How hot do we keep the fuel on the ship, like before it goes into the boiler?
How hot is it? It's pretty hot. I don't remember the exact temperature, to be honest. What I do remember is that you don't want it to get it on you when you're cleaning the fuel strainer, because it's that hot. Is it going to do third-degree burns on you? No, but you're going to have a bad day. But the pipes are nice and warm. All right, so the evaporator, the primary fluid changes from liquid to a vapor. So it's absorbing latent heat, so an evap. All right. And we have a condenser, where the primary fluid changed from a vapor to a liquid. It's giving up its latent heat. And that's why we call it a condenser. That's why we call them an evaporator. All right, that's where those names are coming from. So we have our main condenser. All right, this is back into the steam. All right, we have our our low pressure turbine right here, quite literally connected. There is a piece of pipe here that is not that big. All right, it may be even just about a foot long. It's quite literally nothing. All right, we have our main circulating pump. It's circulating salt water, and it goes directly overboard. So as our steam is going through it, it's turning into a liquid. All right, we have our main condensate pump. We have an air drag line that's going to an air ejector. All right, so what's the point of the air ejector?
Remove non-condensable gases.
Yes. All right. The whole point of it is to make sure this thing stays at 28.5 inches. All right. We want to get this thing to a near perfect vacuum at all times. All right. That means we don't have to have as much salt water going through to cool it. All right. Now, what is another option from this main circulating pump?
Ship has a scoop we can use.
Yep. So it literally is a scoop. All right. It's at the bottom of the hull. And it literally is just a scoop where salt water, we're using the ship's momentum to pick up salt water and push it through the system. It comes through this section and it just gets dumped overboard. It's not mechanical in any way. We have a valve and that's about it. All right. Just know that there is a scoop. So let's look closer into the air ejector. All right. We have that auxiliary steam that's coming through. Remember, this is auxiliary steam that's coming out of the boiler. It's coming out of the superheater. We step down the pressure to 150 psi. All right. This is our vacuum drag line that's coming from the condenser. Who knows where our air ejector is located on board the vessel?
Isn't it next to the low pressure turbine?
Yep. Where?
Uh,
It's next to the low pressure turbine.
Or inboard upper engine room.
It's inboard upper engine room. All right. So it's next to it. If we have the boilers over here, this is our low pressure turbine. Is it on what's here? What's in this spot?
Bullseye.
Bullseye. The bullseye is right there, but what's in this spot?
Low pressure cutout, I think. I don't know.
We have our blue ball strainer. It's a duplex. The boiler is right here. There's our low pressure turbine, and we have let's pull up a bigger whiteboard. If we have both our boilers, a little hallway in between them, all right, and we have our high pressure turbine right here. We have our low pressure turbine. All right, we have our throttle box right here. We have a stern guardian valve right here. We have our lube oil strainer right there. We have our burner bench right here. Over here is the Nyrex. All right, over here we have our TGs and stuff like that, but I'm not going to get into those. So we go across. What else do we have? What's right here?
it's condensers for some like refrigeration or for heating system. I'm not sure.
Nyrex, right? Or
Nope, Nyrex is over here. We have the condensers and everything that you were talking about. Refrigeration system is over here. All right. There was two things. Oh, we got someone in the chat. We have the tools and the Quincy air compressor. Yep, the air compressor is over here. There's some tools. This used to be, at least when I was here, is this still a distillate, an evaporator, a flash evap? There was two flash evaps right here and
I think
here.
they got rid of one of the flash evapes.
I think it was
There's
this one,
one
right?
there's two there now, but one of them doesn't work or they don't use it.
Yeah, they haven't used them since I was basically, who's putting up their drawing? There we go. Someone's thinking. So Our air ejectors are right there. All right. This is the location for our air ejectors. All right. So the big things you guys got to do with everything is just keep thinking about when we're talking about equipment. And I know we've had limited time on board the vessel, but we have to always constantly think of where these things are located. All right. Does anybody need me to keep this up? Okay. Let me go back to the slideshow. Oop. There we go. So basically what we're doing here is we're dragging out, just like we talked about with any of the other air ejectors that we had. We're trying to bring down a vacuum. Okay. So this is our condensate from our main condensate pump. All right. Keep that in mind, our main condensate pump. So our air ejector is coming, we have something coming right from our main condensate pump. All right. So again, we have another heat exchanger. We are increasing the temperature now of our condensate. It is now a liquid, but we're now trying to increase our temperature slowly. All right, because we have 150 PSI auxiliary steam that's very hot. We can't use that steam anymore because it's mixed with non-condensables. So we are basically trying to gain as much energy back from the system as we can. And after that, we go to our first stage heater. To the first stage heater. All right. So this is coming from the air ejector. Now, we haven't used the first stage heater on board the vessel, at least the entire time I've been here. All right, we basically bypass it now. All right, this is basically, all it's doing is just being like a first stage. It's supposed to increase efficiency with this. All right, we're utilizing some turbines, basically the low pressure turbine bleed. We're getting some steam that's going through it, and it's increasing the temperature of our condensate going from our air ejector to the DC heater. You know what? Let's stop at the main air ejector for today, because it's 11:12. So we're going to go through slides 1 through 24 is going to be on the quiz.
Wait, what slides again?
1 through 24. All right. Does anybody have any general questions before we end it for today? No? All right. That is it, guys. At least what I have for you today, since we're just ending like 2 minutes early. All right, so quiz Monday. All right, and there is no test Monday. I want to make sure that it's reiterated. There is no test Monday. All right. Again, if you have any questions on your grades or how that grade was achieved, you can always come to the office hours. All right, or email me. I'll be happy to show you the math behind it. All right. Other than that, I will see you guys Monday.
I have a question real quick.
Yeah.
So with the third exam, is that going to be the same time as the final or the same day just during this time?
So it's going to be 50 questions. It's going to be normal time limit, hour 15. So that way, if people need the extra time, they can have the extra time for that day. It'd be a lot easier to implement that. But it's just going to be an hour and 50-minute question test. All right. It's not cumulative. It is only the 3 sections: electricity, hydraulics, and steam. Okay.
Okay. What time is it? Like, what time are you going to have it?
Oh, so it's the final we have is from 8:30 to 9. I think I'm just going to do like a 9 o'clock, 8:30 to 12. I'm sorry. I think I'm going to do like a 9 o'clock start. All right.
All right.
That
Thank
will
you.
give an hour and 15. So it's to 10:15. And then the people who need the extra time will fit that perfectly. All right. Anybody else have any questions? Well, not, I'm releasing you guys.
Thank you.
Have a good weekend.
Sounds good. Thanks.
You.
Oh, yeah, Christopher. I don't know anybody at those what do you call it? At those shipyards, by the way. I don't want to leave you hanging.
It's all right.
So if you know someone on those, I'd pursue them if I were you.
The problem is that a lot of them just, if I had been able to go maybe a month ago, they might have taken me. But now they're all terrified, especially if I say I'm from Maritime, which is in the middle of New York.
Yep.
Yeah, so I
about-
can try maybe without even knowing if we're going to have like I've been told, yeah, we might leave in June 15th. Who knows? I really can't do anything right now, which kind of sucks. But
Do you have let's see. You have your Twig, but what about any of the ferries or anything? I know you just want some sort of experience, but are you on the island or Connecticut area?
I'm in Connecticut. I just want experience, but either places are all shut down, including all the design offices I was, have
Mhm.
connections at, or, no ship or ferries taking anybody right now. Not a single one. And then most of the shipyards, although they're still burning day and night, they don't want to take anybody new.
Yeah. That's basically where the world is at right now with this.
That's what it is. But
Yeah, I know there's a lot of people out there itching for some sort of experience in something. So,
yeah, I mean, I'm waiting for them to tell us, yeah, we're having a fall cruise. So good luck figuring that out. So I'm not even going to start planning ahead for that stuff until I know more.
like I said at the beginning of this, act like it's INDOC. Take a day at a take that day's worth. The plans change, just roll with it. Honestly, this is how shipping works anyway. You could be out to sea for like four months, and then all of a sudden they're like, "Hey, you know what? You know that day that you were looking forward to that you were supposed to go home? Nah, that's not happening." And there's no reason why.
We'll see. Actually, I do have one question about your slides. You said that the stern turbine had Curtis and an impulse. I
Yeah.
thought Curtis and impulse was the same thing. because I did go over turbines a long freaking time ago. And I remember learning something about Parsons and reactions were tied, and Curtis and impulse were tied together. They're basically the same thing. What's the difference between a Curtis and an impulse?
So I'll have to get back to you on that. All right. Because the same thing with me is I haven't gone in depth into turbines in a while. All right. But I know that they're separate from each other. So there's two different stages in there. All right. So they have one Curtis and one impulse. Even though it doesn't seem to be drawn right on there. But
yeah, I saw, but I'm surprised that there's not more reaction stages inside the HP turbine, but I never really got in depth into how they work, just the basic concepts, like the actual practical application.
if you're really that interested, the turbine book that you get your senior year is always very good. It's a textbook. You know, it's not like it reads like anything nice, but it's the.
I mean, you saw the Harrington book that I read, fair portion of, so whatever.
Yeah.
Doing anything else with my time here? Holy Christ!
Yeah.
Going out of my mind.
Yeah, you can take up some of my job if you want, but the naval. It's basically, I think it's called the Naval Turbines book. It's up in my attic right now, but they're really good. They haven't changed in forever. The guy who wrote it used to teach at Maritime.
Oh, well, what was it, Rowan? Or
Yep.
he went to Webb for a while. I remember him. He was a nice guy.
Yeah, he was something else. He used to come out of that class being able to design naval turbines. See if I can find it. No, that's modern marine engineers. It's modern marine engineers also. I don't want those. Yeah, I can go get it if you want me to.
No, it's all right. I got to run to my dynamics. Go to my dynamics class anyways.
Yeah.
But I'll look it up. I probably could find a copy online or find somebody who knows the actual ISBN, so it's no big deal.
All right. I don't know why I can't seem to find it easily.
Big deal. But thank you. Have a good day, and I'll see you Monday.
I will see you on Monday. Anybody else have any questions? All right.